Okay, so let's get started. So this is lesson 15. So before we start, let's just kind of do a recap, because I didn't really do a recap of the equations of lines that we saw. Let's take a look here. So we have this idea of, instead of using slope to define the direction of a line, we use a direction vector, which is a vector parallel to the line. And then from there, and if we look at this diagram here, we were able to describe the points on the line by setting it up as a sum of vectors. So you take the vector to, you can't see the screen? Sorry, you're not seeing the screen?
I can.
Yeah, we can see it.
Oh, that's
Yeah,
odd. Some of
okay.
you are not seeing it. Yeah, so I'm presenting, so I'm not sure what's going on. If, yeah, maybe try going off and coming back on. Okay. Okay, so if we take a look at this diagram here, we see that we set it up as a sum of vectors. We take the vector to a given point, all right? And then we add some multiple of this direction vector, and that brings us to another point on the line. If I add a different multiple to another point, and so on and so forth, all right? So one way to write it out is in vector notation. The other way is to write out the vectors explicitly, all right? But we also saw these other two forms. So the parametric form is essentially the exact same thing. The only difference is we're individually writing out equations for the individual components, and we're going to see in, certainly one of the questions today, how that's going to be a useful form to work with. Okay, and then there's this one here, which is not really particularly useful, but it is a form that the textbook likes. And the idea is you just solve for t in each of these equations, and you get these three formulas. Okay, and since t is the same in all three equations, you can just equate them. Okay, but the idea here is to be able to recognize that when it's in parametric form or symmetric form, that the constants represent your coefficients of the, the components of your given point, all right? And then the coefficients of t represent the components of the direction vector. In symmetric form, okay, this number that's being subtracted from x, y, and z are the components of your given point, and the denominators represent the components of the direction vector, okay? So the reason why we introduced this new way of defining a line, because you had great ways of defining lines in 2D, is because this is the one that upgrades nicely into 3D. All right. The other versions, at least from what we've seen so far, do not upgrade very nicely to 3D. All right. So what I want you to do is take a look at these two questions. Okay. And even if you don't solve them completely, I want you to try to set it up. So let's take a look at the first question. So it says find a vector, parametric, symmetric equation. So just give all three of the line that passes through -642. So that's good. One of the things you need to find the equation of the line is a point on the line. So check, you got that. But this is interesting because they're giving us information. It says that the line you're looking for is perpendicular to these two other lines. All right. So clearly the other piece of information you're looking for is the direction vector of the line you're trying to find. The question is, how can you use this piece of information to find the direction vector of the line? Okay, so think about how you'd set up this question. And then number two, well, talks about a sphere, which again, we've seen. You should have done that in the previous assignment. You should know how to set up the equation of the sphere. So I'm hoping you don't have to actually calculate the equation of the sphere. You should be able to just write it out. And it asks us, how many times does this line, this 3D line, intersect the sphere? So think about how you would set up a solution for such a problem. Okay, folks, we're back. So let's take a look at this first question here. All right, and nothing stops you from drawing a little diagram. So you've got these two lines, in 3D. And what you're looking for is a line that's perpendicular to both of those. So we have a point on the line that we're looking for. What we're missing is a direction vector. So how are we going to find a direction vector that's parallel to the line we're looking for, but perpendicular to both of those two lines? So I'm looking for suggestions here.
Could you take the cross product of the two lines you're given?
There you go. It makes sense to take your two direction vectors, which are in the same direction of the lines, and if you take their cross product, then that should give you the a vector, because remember, you need any vector that's perpendicular to both. Okay, so that's the first step here. Well, actually, that's maybe the second step. The first step is to identify what your direction vectors are. Now, these are both given in symmetric form, so we recognize the denominators as representing the direction vectors. So what we're doing is we're taking the cross product of -4, -6, 3, and 3, 2, 4. Okay, so -4 and 3. So I'm going to do this quick. Make sure you're checking my algebra here. So the direction vector that we're looking for, okay, so what do we have? We have -24 minus 6, so that's -30. All right, here we've got 9. It's going to be plus 16. That's 25. And then here we have -8 minus, what is it? -8 plus 16. Sorry, -8 plus 18. What is that? That's going to be 10. Okay. So here's the cross product of my two vectors. Do I have to use this vector though? What could I use instead? That would be simpler than this one here. I could certainly use this as my direction vector, but this is not what I'm going to use. Can somebody tell me some other vector that might be simpler to work with?
6, 5, or -6, 5, 2.
There you go. You might as well take a simpler parallel vector to this one here. So if I multiply this vector by 1/5, okay, because of a common factor of 5, I end up with -6, 5, 2, which is parallel to this vector, hence can also serve as a direction vector. Okay, and so now I can just start writing my answers. My vector form is just going to be, well, my given point, which was -6, 4, 2. Whoops. -6, 4, 2 plus t times my direction vector, which is what I just found here, -6, 5, 2. And I need to specify here that I'm taking all values for t. Okay. And then similarly for parametric form, well, x is just going to be equal to -6 minus 6t. Okay, y is going to be equal to 4 plus 5t. And then z is going to be equal to 2 plus 2t. All right. And lastly, if I want to put it in symmetric form, well, it's going to be x minus the x value of my point. So x minus -6 is going to be x plus 6 over the x value of the direction vector. Okay, equal to y minus the y value of my point, so y minus 4 divided by the y value of my direction vector. And that's equal to z minus the z value of my point divided by the z value of my direction vector. Okay? So, like I said, these are the two versions of the line that are going to be most useful to us. But like I said, the textbook does tend to give a lot of the questions using symmetric form, so it is a good idea to be able to recognize it and be able to work with it. Okay, any questions on this one here before we move on? Okay, so last thing I'll say here is I want you to think about this in the same way that I think about finding the equation of a line in 2D. Okay? Why do we need to specify? Well, because it's this number that's going to then be the one that produces all the numbers on the line that we're looking for. Okay? Because it's not something we're really going to get into in this course here, but you could imagine sometimes that you might just be interested in one segment of the line. So you might only be working with the t-values from 0 to 10 or 0 to 1. Okay, this specifies that we're working with any t-value, meaning we're looking for the equation of the whole line. Okay? So let's take a look at number 2 here. So first of all, we have to remember how to come up with an equation for the sphere. Okay, presumably if we want to try to find something like an intersection, or notice here, do you notice, did we ask for the intersections themselves? Notice that all I asked was the number of times it intersects. So keep that in mind as we're doing this. So who can tell me what the equation of the sphere should look like? So I'll start writing parts of it out, and maybe people can tell me what should be in these missing components. So what do you think I'm putting in this component here, in this part here? There you go. Is you have x, y, and z. These are all going to be squared. Here you're going to have the radius squared, so 25. Okay, and then these numbers here represent the center of your sphere. So -1, -1, -1. Okay, so the idea here is we've already established this concept. We don't need to reinvent the wheel. Okay, but look at what I find in my equation of a sphere. I find the x component separate from the y component, separate from the z component. So if I want to try to work with this sphere and this line, what do you think might be a useful thing to do when considering the equation of this line? There you go. Let's write it out in that form that gives us the x, y, and z components explicitly. Okay, so here let's take a look at what this would be. Well, it's 0 plus t. There you go, just t. This would be 1 plus 2t. Okay, and here we have 2 minus t. Okay, and what is special about the intersection of two objects? So tell me, what is special about when we talk about intersection? What is special? So you're giving me more how we're going to go about doing it. I want somebody to explain to me what is special about the places where two things intersect.
They're equal?
Yeah, they're equal. They share the same points. So essentially, we're looking for those points where this x, y, and z and this x, y, and z are equal. And hey, that sounds a lot like solving an intersection problem or a system of equations, and that's essentially what we have. It's not a linear system, but it is a system of equations. And so usually when it's not a linear system, more often than not, substitution is the way to go. And so I think that's a good idea for solving this problem. Wherever I see an x in this equation, I'm going to substitute it by the expression of x, y, and z from the parametric form. So let's see what we have here. X is equal to t, so -1 squared, plus y is 1 plus 2t, and then -1 squared, plus z is 2 minus t, -1 squared equals 25. And lo and behold, what type of equation is this? Now that the only thing I have left is t as a variable. What type of equation does that represent now?
Quadratic.
It's quadratic. So now we know that quadratic equations, sometimes have no solutions. Maybe this line, and if you think of, I didn't think of bring a ball here. Let's see, do I have, unfortunately, I've got nothing spherical nearby, but let's say here, this represents a sphere, and you can imagine that the line could maybe never intersect the sphere. Or maybe the line could be just tangent to the sphere and it only intersects once. Or the line could go through the sphere and it intersects at two sides. Okay? So not surprising when you think of it physically that we would end up with a quadratic equation. Okay? So let's just quickly go through this here. What do we have? We have t squared minus 2t plus 1. Here the ones cancel out, so I'm just left with 4t squared. Here, what do I have? 2 minus 1 is 1, so I just have 1 minus t squared. So 1 minus 2t plus t squared equals 25. So let's see what we have. We have 4, 5, 6. Okay, negative 2 minus 2 minus 4t. And then what do we have? We have 1 plus 1 is 2 minus 25 is negative 23. And there's my equation in a much nicer form. And do I need to actually solve this equation? So look
No.
at what
No,
they're
no,
actually.
you don't.
No,
You just have to know like the amount of times it goes through the sphere.
There you go. The only thing that now, if they were asking me, when, what are the intersection points? So I'd have to solve for t and then input it into one of my equations. But here, all they want to know is how many times. So yeah, I'm going to use a discriminant. So, use the discriminant is equal to b squared. So negative 4 squared minus 4 times a times c. Okay, and here I have 16 plus some number. So this is definitely greater than 0. All right. And so, okay, 2 values of t, which means it intersects twice. Okay. And there you go. And what's nice about a question like this is how you see, again, that, when we talk about building up, a set of algebraic tools from grade 9 or grade 8 all the way to grade 12, we see how these tools that might have come up very early on are still very valid, even when you're dealing with something much more complex, like intersections of lines and spheres. All right? So definitely keep this one in mind. I feel as though this might come back to be useful for us at some point. All right? Any questions on these two that we want to ask? Okay? So main thing here, I would say, is make sure you're very familiar with the 3 versions of the equation. Make sure you're familiar with how to find the particular information, what represents the, direction vector, what represents a known point on the line, okay? And then try to recognize which version of the line might be more useful at any one point, okay? So,
sorry, Tony, could you just justify why the value for t directly translates to how many times it intersects?
Oh, because here now, this equation represents equating the x and y's. So now 2 different values of t, which are going to produce 2 different points, okay, will match both this equation and that equation. So it means that these 2 equations will share those 2 points, because these 2 values of t were gotten by assuming that the x, y, and z's from the line are the same as the x, y, and z that will appear on the sphere. Okay, does that make sense? Okay, great. All right, so let's move on to now. Pretty great. We've got all these different ways to describe equations of lines in 2D, and we kind of did what we need. So we had equations of lines as done in grades 9 and 10. Perfect to solve those types of equations. We brought in this new one, the vector equation, to help us upgrade to 3D. Why in the world would we want to look for more equations of lines? Okay. And the answer to that, unfortunately, won't necessarily come today, but I'm going to ask you to trust me that while this may look like a bit of a, especially once we get to the end of it, might look like a bit of a waste of time, you'll have to trust me that we're doing this in preparation for something else. All right? And maybe you might even recognize what this is in preparation for. But what I'm claiming here is that instead of coming up, so it's still going to be a vector-based equation, but instead of using a vector that's parallel to the line, okay, we're going to try to come up with an equation that involves a vector that's perpendicular to the line. Okay, and we're going to keep our discussion to 2D for now. Okay, so let's take a look at what this might look like. Okay, so I'm living in 2D here, and I've got some line, and what I want to do is, instead of using a vector parallel to the line like I did before, I'm going to use a vector that's perpendicular to the line. Okay, so if I were to draw it, I can move it anywhere I like. So if I call this, this vector perpendicular to the line. Now, who remembers what we call a line that's perpendicular to another line? It's something we saw. Sometimes they would ask you to find this line back in some calculus problems. So I'm waiting for an answer. I'll just clean up my diagram. I don't like that. Not straight enough. Okay. Okay, well, somebody's got it. That's what we call the normal line. Okay, so it's something that sometimes came up in the calculus course. They said, instead of finding, the slope of the tangent, find the slope of the normal. Okay, so not surprisingly, we call this a normal vector. But as before, when we were working with parallel vectors or direction vectors, this is not the only line that's perpendicular to that vector. This line is perpendicular to that vector. This line is perpendicular to the vector. Lots of lines are perpendicular to that vector. So what else do you think we're going to need if we want to try to use a perpendicular vector? And what should we expect to also need? There's lots of lines in 2D that are perpendicular to that vector. So what am I going to need to precisely talk about one particular line? There you go, a point. Okay. So let's say, remember, we can place our vector anywhere. So I'll place my vector at this given point, which, as before, let's not reinvent the wheel. Let's call that x naught, y naught. Now, I give the hint here that we're going to use one of the products here. Now, can you sort of see that there's a product we can automatically eliminate? Which of the two products that we've defined can we eliminate? There you go. We're working in 2D. We know that cross product is not even defined in 2D. So, if we're going to work with a product, I guess it's going to have to be the dot product. Oh, I guess it could have been scalar multiplication, but usually when we say product, we mean either cross or dot. Okay. So what I want you to think about is, this is the vector n. What relationship might it have to some vectors that are related to this line? Okay, because we'd like to, if we're working with this vector n, we'd like to find some relationship with other vectors. Can anybody see what relationship it might have with some of the other vectors related to this line? Let me give you a hint. Presumably, our equation that we come up with is going to involve some random point on the line that we're going to call xy. So interesting. We're saying that the dot product is equal to 0. So what dot product? Be more specific. So we're talking about the dot product. That means we're talking about two vectors. Which two vectors will have a dot product of 0? So I'm going to add a little something to this diagram. Well, yes, the line and the normal, but the line is not a vector. But what if I create a vector between these 2 points? Can we see that these two vectors have to be perpendicular? Okay, very good. And hence their dot product is 0. Does it matter if I had chosen this point as my xy? Sorry, I lost the chat. No, because let me draw this vector. Hey, still perpendicular. Let me choose that vector, still perpendicular. Let me choose this vector, still perpendicular. So regardless of what my choice of xy is, when I go from x0, y0 to that point, the vector that is formed is always going to be perpendicular, okay, to the normal vector. Okay, so we can say that vectors n, the normal vector, and vector from x0, y0 to xy have to be perpendicular. And that allows us to set up an equation because we know that perpendicular vectors have a dot product of 0. So this is how we're going to develop yet another different, presumably, way of defining the equation of a line. So let's just see what happens here. Okay. So I called the direction vector little a, little b. So I don't know, I guess let's call this one, just to distinguish it, because I don't want to use the same letters, let's call it capital A, capital B. Okay, so what we have here is we have that the vector AB, which is the normal vector, dotted with the vector joining these 2 points. Okay, notice how I chose to go in this direction because I'd like the variable to come first because it's second minus first. So this vector is going to be x minus my given x value and y minus my given y value has to be equal to 0. Okay, and this in principle would be a a reasonable equation for this line. Okay, it's what we call the Cartesian equation. But can you see that it would be nicer if we kind of did a little bit of work and simplified? Okay, so again, you should follow around. Hopefully, you're writing this out. So let's simplify this here. Let's take the dot product. So multiply the x components. So a times x minus x naught plus b times the y component here, y minus y naught equals 0. Okay, might as well keep going. Let's distribute here because these are now just numbers. Ax minus ax naught plus by minus by naught is equal to 0. It's funny, now that I'm looking at this equation, is it not starting to look a little familiar? I mean, maybe it's a little messy, but is it not starting to look like something that you already know? Be more specific. Which equation of the line? Yeah, this is starting to look a lot like the standard equation of a line. So let's clean this up a bit. Let's see if we can make it look even more like that. So here, ax, remember x represents some variable because it's any point on the line, plus by, again, y is variable because it represents the y component of any point on the line. But these 4 values are all given numbers because a and b represent the components of the normal vector, which presumably I have, and x naught, y naught represent the components of a point that I know already to be on the line. So what I'm going to do is I'm going to join all of these together. Okay, can everybody see that going from here to there, perfectly legal? I didn't do anything funny. Okay, but guess what I'm going to do now? Guess what I'm going to call this whole expression full of known values? I'm going to call that C. And lo and behold, this newfangled way of determining the equation of the line actually produces an equation that we were already familiar with. So now we see that standard form, what we used to know as standard form, is the same as, that means is equivalent to, what we now call Cartesian form, the Cartesian equation of the line, sometimes also called the scalar form, but this is the more common one, okay? Except now this equation has a physical meaning that we did not ascribe to it back in grade 9 and 10, okay? What is special here? What is the physicality that now exists in this equation? There's a couple of these letters that now represent something very specific. Which two letters represent something specific about this line? There you go. A and B, the coefficients of x and y, represent the components of the normal vector. Okay, so here we could say where AB is a normal vector to the line. All right. So in the end, this turned out not to be a new form of the line, but it's certainly a new way of looking at this standard form or Cartesian form of the line. Okay, it turns out that this number A and this number B, so now you can sort of see, it's not by accident that I chose those two letters. I knew where this was going, but now you have a different view of this standard form of the line. A and B represent a normal vector to the line. Okay, so what I'd like you to do, and this should be, okay, don't overthink this one, it should be very quick. If I give you the point on the line and I give you this vector that's perpendicular to the line, how could you quickly calculate this Cartesian or standard equation to the line? Okay, so we're back here. So what's a quick way we can do this problem? Okay. What do you think the first thing is that I'm going to write, given that I know that I'm looking for the Cartesian equation? There you go. Is I'm going to start with the fact that I know that the equation has the form ax plus by plus c equals 0. So right away I know that because the line is perpendicular to this vector, this is going to be my normal vector. So that means a is equal to -4, b is equal to 3. But so what I'm looking for now is the c value. But what other information do I have beyond just this a value and the b value?
You have x naught and y naught.
There you go. I have a given point on the line. So that means it has to satisfy the equation. So with the point 2, -5, and I know the normal vector, which is my AB, is equal to -4, 3. I can just stick everything into the equation, kind of like what you do with, slope-intercept form. You stick everything into the equation, and the only thing left to solve for is c. Okay, so here we have -4 times the x value is 2, plus the b value there is 3 times the y value there is -5 plus c is equal to. So c is just equal to. So what do we have? We have -8 minus 15. So that's -23. Bring that to the other side. C is equal to 23. So what's our equation? It's -4x plus 3y plus 23 is equal to 0. Okay. And if you want to make this first one positive, which is often what we do, but I'll be fine if you leave the negative there. You could write it as 4x minus 3y, minus 23 is equal to 0. That's also good. Okay. So once you have the normal vector and the point, finding the equation is a fairly quick process. Okay. So do not forget, yes, we came to the same, result as something we had already done before, but do not forget this whole process, because we're going to see that, like I said, this wasn't so much about coming up with, the equation of the line as it is
Tony,
you know, something that we're going to get later on. Yep.
I got 31 for my C value.
Whoops. Let me check. Maybe I'm doing that too quickly
Oh, wait,
here.
no, I used wrong numbers. Sorry.
Oh,
I just
okay.
copied the 2 down as a 4.
Okay, there you go. That makes sense. Yeah, because -8 minus 15, that should be -23. All right. So I need to stop right at 3:30 because I've got another meeting to go to. So I may, instead of giving you time to work on things, I think I'm just going to have to just kind of teach through it here. So this is something I want you to think about this here, because one of the things that you're going to see questions that come up are, like we did before, going, you know, from say parametric form to vector form or symmetric form. Sometimes we want to go between Cartesian form, vector form, okay? And there's a quick way to take a normal vector and turn that into a direction vector, or to take a direction vector and turn it into a normal vector. In other words, is there a quick way to take a vector and to determine a perpendicular vector? So let's say I take this vector here. Okay, actually I just realized I should have given myself a little more room here. Okay, let's say I take this vector. Let's take something specific here. Let's say I take the vector, say this is 4 and 2. So the vector is the vector 4, 2. Okay, and what I want to do is I want to create perpendicular vector. Can you see visually what relationship there's going to be between these two vectors because of this 90-degree angle here? There you go. You realize that the side lengths should be the same, okay? That these are going to be similar triangles, okay? So this length, which is the base, used to be the height, is going to be 2. And this height was the base of the previous triangle, okay? Except we notice that in the x direction, it's actually going to be -2. So it looks as though we're flipping the two components and making one of them negative. But wait a minute. Do I have to make this one negative? Can somebody see how I can achieve another vector where I'm still switching the components of x and y, but I'm making the y the -1 and keeping the x positive? How would I draw it?
Take the normal in the other direction.
There you go. What if I draw this vector here? The opposite vector, you realize that now the 2 is positive and the height now is going to be negative. So either of these two vectors is going to be perpendicular to that given vector, okay? So if you have some vector, let's call it xy, okay? Two vectors that are perpendicular to vector u are, well, what did we say? We have to swap the components and make one of them negative. So this would be one option, and this would be one option. Okay, so again, this vector 4, 2, a perpendicular vector was -2, 4. Another perpendicular vector is 2, -4. Okay, and there you go. You've got a nice, easy way to take, say this was a normal vector to a line, and you were looking for a direction vector, so it has to be perpendicular, you can use this trick. Or if this represents a direction vector, and you're looking for a normal vector, you can use this trick to easily do it in 2D. Okay, so let's see how that might come into play here. Okay, say, for example, in this question, they give me an equation in parametric form. And they say write it in Cartesian form. So what's the first thing? What is it that I want to extract from this equation? What are the two things I'm going to extract from this equation to help me solve this problem? There you go. I know I'm going to need a specific point to find Cartesian form. And so this is where I'm going to look at those constants. And I realize that a point on this line is going to be -7, 4. Perfect. But now, Cartesian equation, I still need a normal vector. What's going to help me find a normal vector here? There you go. I'm going to extract my direction vector, which is the coefficients of t, so 4, -13. And how do I take this direction vector and turn it into a normal vector? In other words, a vector that's perpendicular? Well, hey, I'm going to use that trick we just saw. I just have to switch the components and make one of them negative. So I could use -13, -4, which of course is not what I'm going to use, because I'd like to, if I have the choice, I'd rather work with positive numbers. 13, 4, I know based on what we just established, must be perpendicular. And so now I have the information I need to determine the equation of the line. So this is A, 13 times the x value, -7, plus B times the y value, which is 4, plus C equals 0. And so here, let's, I'm not going to bother doing this in my head, even though we should certainly be able to. 13 times -7 plus 16 is equal to -75. Bring that to the other side. So 75. So what's my final answer? 13x plus 4y equals 75. Okay. Now, I think for now, just to kind of, in the interest of time, I'll leave this one for you to finish, and the solutions are already posted online. This is kind of the opposite. Here, if I want to find the vector equation, I'm going to need a point and a direction vector. Well, presumably you will use your normal vector, which is 2, -3, to turn it into a direction vector. And how could you find a point on this line? It's not given explicitly. What's the easiest way to find a point on this line? Who's going to remind us? There you go. Input a value for x and solve for y, or input a y value and solve for x. And what are usually the easiest values to input? I'm hoping somebody's going to say 0. Yeah. 1 or 0. But in this case here, I'd say 0, because look at the coefficient of y. It's a factor of 9. So I would pick x equals 0, and look how easy it is to solve for y. So again, try to always go for the easy route, at least when it comes to the arithmetic stuff. Okay, so I'll leave this for you to finish up. And the last thing we're going to do for this section here is finding the angle between two lines. Okay, so let's say two different lines. Oh, yeah.
The question back up at question 6.
Yep.
Shouldn't be 13x plus 4y is equal to -75, or no?
Oh no, because here what this addition is equal to -75. So when I solve for C, it becomes +75. Oh, sorry, I see what you did. Sorry, it's the mistake that I made wasn't the sign. The mistake was I didn't want to put that. Thank you very much. Good catch there. Sorry, I wanted to put the 75 there. I could have put it on the other side, but I want to stick to, this is sort of the book's standard, so I'm going to stick to that. Thanks for noticing that. Who was that, Charlie? Thanks.
Yeah.
Okay. Okay, so last thing. So again, let's say you have two lines that represent sort of two routes that are being followed by different objects, and you want to determine the angle between those two trajectories. Well, you'd be looking for the angle between the two lines. Okay. Now, there's certainly, I would say, the easy version of this. Okay, so here I've got, two lines. And the easy version, I would say, is if you have the two equations given in vector form, so that you have two direction vectors. Because if you have two direction vectors, place them tail to tail, and hey, look at that. The angle between the lines is the same as the angle between the two vectors. And it's very easy to find. By the way, let's remind ourselves, how do we easily find the angle between two algebraic vectors? Quick. Yeah, there you go. Don't even hesitate. You use the dot product. Can you see a little issue, though, that might arise? I kind of drew this diagram very nicely. Yeah, but if the lines don't intersect, what would you notice about the two direction vectors? What would be special about they'd be parallel? So you'd actually know that even before that. So good point, and in which case, I guess the angle between them would just be 0. Well, the little issue here is it kind of makes sense that if I'm determining the angle between the lines, or there's technically two angles between the lines. There's this one here, which I call theta, and this one there. I don't think you're going to be too surprised that the one that we choose to represent the angle between the two lines is the acute one. But what if it so happened that the direction vector for this second line was this one here? When you find the angle between these two vectors, you're going to get an obtuse angle. Well, guess what you have to do if you get an obtuse angle? If you happen to get this angle here, no, you don't cry. How do you make it acute? We can't just say it's acute. What do? What is the relationship between these two angles? There you go. So if you happen to find this angle and you say, oh, that's 127 degrees, that's not the one that I want, you just, 180 minus phi, if that's the case. Okay? So nice and easy if you have the direction vectors. What if, though, you have two lines given in, what if your two lines are given instead in standard form or in Cartesian form, meaning you have the normal vectors like you have here? Well, you could change the normal vectors into the direction vectors and then, just find the angle that way. Or maybe there's a relationship between the normal vectors. So say this is normal to that line, and say you've got this here, which is normal to the other line. Here's the angle between the vectors. Is there an angle between the normals? Now, somebody is claiming that they will be the same angle, but of course we need to justify that. Okay? And by the way, you would be correct, but let's justify it real quickly. All right? So here, if this is theta, the angle between the two lines, well, this angle here, hey, 90-degree angle. This would be 90 minus theta. But now I want you to look at this right angle. If this is 90 minus theta, this angle, which is the angle between the normals, would be 90 minus theta. So 90 minus this angle here. But what is 90 minus 90 minus theta equal to? Well, 90's disappear. Negative theta is just equal to theta. And so what we see here is finding the angles between the normals is equivalent to finding the angles between the angle between the what's that called? The direction vectors. Okay. And maybe just to end off, I'll just do one of these. Let's do maybe part C, because it's got a bit of everything. Okay? Oh, I got that here because here I've got a right angle triangle. So if this is theta, this is 90 minus theta. Okay? And then here, I now work with this right angle here. If this is 90 minus theta, this is 90 minus that one. Okay? Does that make sense? Okay, well, if it doesn't, I got to do this quickly here. So let's just do this one quick. Well, I notice from equation 1, whoops, that's equation 1, I have this normal vector, which is 6, -5. Okay, then from my second one, I have a direction vector, which is 1, -1. But how do I take that direction vector and turn it into a normal vector? Well, just flip them around and change the sign of one of them. So there you go, 1, 1. And now I can find the angle between these vectors because 6, -5 dotted with 1, 1. The dot product is equal to the magnitude of the first vector. So 6 squared plus 5 squared times the magnitude of the second vector times the cosine of the angle between them. Okay? And I can solve for the angle. Okay? And you can check the solutions online. All right? So in this case here, you have two direction vectors. You can just find the angle between them. Here, you have two normal vectors. Just find the angle between them. Here, you needed to do a little bit of work to end up with two normal vectors, or you could have also worked with two direction vectors. All right?